We've already seen a physical equilibrium, and in this experiment we're going to look at chemical equilibrium. So to start, I'm going to consider the equilibrium that we already know about, and that was when liquid water is at equilibrium with its vapor. Remember when we talked about having a closed container? If the container is open, the liquid water will just leave. As it evaporates, it will just leave. But if you close the container, what happens is that as the water evaporates, it builds up, and then some of these molecules occasionally will strike the surface, and once there's enough built up in here, you'll reach a state where it's evaporating at the same rate that it's condensing. So a few things about this equilibrium is that nothing has stopped. There's still reaction going in both directions, evaporating and condensing. And so we show double arrows like this. Also, we're not saying that there's equal amounts of liquid and gas. There may be a lot more in the liquid phase than the gaseous phase. Okay, let's imagine, what if we took this and we warmed it up? How would that change the equilibrium? Well, what it would do is give the particles more energy, so they would be more likely to vaporize. So maybe more would have to vaporize before the rate of condensation could make up for that. In other words, we would reach a new equilibrium where there's more in the gas phase, but it still would come eventually reach equilibrium. Okay, let's look at, so we have two equilibriums, and in a sense we would say this equilibrium shifted toward the gas. In other words, we're saying when we look at this reaction, we're saying that heating it shifted the equilibrium toward the gas. It doesn't mean that it all became gas. It just means that there's more in the gas phase than before. Well, let's look at why that is true. If we look at the heat of this reaction, it is a positive number. Okay, and so positive heat of reaction, that means it's endothermic, which means energy is a reactant. That's how you can think of it. Okay, so if we want to, we could just pretend like energy is over here. And now we're going to apply Le Chatelier's principle. Le Chatelier's principle says that if you apply a stress to a system at equilibrium, the equilibrium will shift to replace that stress, or to undo that stress, to relieve that stress. And so if the stress is more heat means more energy. And for this equilibrium reaction to get rid of energy, it's going to shift to the right. Okay, so once we decide where energy goes, reactant or product, if we're adding heat, it will shift in the opposite direction to get rid of that. That's at least how the reasoning works. We know on a molecular level how it works, thinking about the particles having more energy and therefore they vaporize. But we can look at any reaction and kind of say, well, if I add more of this product, it'll shift to the left. And if I add more of these reactants, it'll shift to the right. And that's what we're going to be doing in today's experiment. So let's go back up here and fill in some things. So equilibrium, we've already defined that. At equilibrium, the concentrations of reactant product are not the same, but they remain constant. And so, for example, if we're looking at a chemical equilibrium, we're going to say that we're not saying that these concentrations are equal. And I want to remind you that the brackets are for concentration. Oops, I'm missing. Measured in molarity. So when we say use the brackets around A, that means the molarity or concentration of A is not necessarily equal to the concentration of B, but once it's at equilibrium, the concentration of A is constant. Okay, and so the stresses that you can have, it can be an energy stress like heating or cooling, but it also could be a reactant or product that is added or removed. In a lot of the reactions we're doing today, the reactants have colors, and that's how you can tell how the equilibrium is shifting. So on my examples, like on this one, this clear means that A is colorless, but B is blue. And C is colorless, but D is red. And so on this one, it says when A and B are mixed, so we mix these reactants, the solution is purple. And if you don't know, purple is when you combine red and blue. Okay, so we mix red and blue dyes, we get purple. So that tells us that starting off at equilibrium, we have similar amounts of reactants and products. And while we're at it, let's look at this energy term. This energy term, that's an endothermic reaction. So energy is a reactant. Or you could think heat is a reactant. Okay, so let's look at what happens in these situations. If I add extra A, so I add A, it's going to shift equilibrium to get rid of that, so it'll shift it to the right, or this way. And what will the color change be? Well, if equilibrium shifts to the right, we'll get more red. It may just be a more red-purple, but it may be totally red. If we add more C, so we've got our solutions and we're adding some more C to it, to get rid of more C, it'll shift to the left, and that will make it more blue. If we remove C, so this one's different, if we do something to take this away, to lower its concentration, and that can be done by having C react with something else, the reaction will shift to the right to replace it. And then last, if we add heat, remember heat is like a reactant since it's endothermic. So if we add heat, it will shift to the right to get rid of it. Okay, so you can figure these out just by looking at the reaction and seeing how to undo the stress. And by the way, when you have the stress, the equilibrium does shift to give you more red or whatever, but it doesn't go back to what it was before. The shift in equilibrium helps kind of buffer that change. It doesn't get rid of the change. In some of the reactions, we use acid and base to get some of the effects that we do. And so let me put it down here. You need to know that the main reaction with an acid and a base, what's happening is that these two ions come together to make water. Okay, so if we're doing an equilibrium thing and we add hydrochloric acid, that is a way of adding hydrogen ions. These come from an acid and these come from a base. Okay. Well, if you add hydrogen ions to any aqueous solution, that has the effect of removing hydroxide. So this is one of the ways we can remove a reactant or product. The other is, of course, we could add sodium hydroxide, which adds hydroxides. But if you add hydroxides, that will remove hydrogen ions. Let's look at another example. HA is an acid. We use, of course, hydrogen in front because it's an acid. The A stands for anion, the negative ion that goes with it. Anyway, it ionizes very little. In other words, at equilibrium, most of this acid is in this molecular form with very few ions present. And so at equilibrium, the solution is blue. On this, I have it marked that HA is blue and these two are colorless. So even when it's at equilibrium, it's mostly blue, and there's just a few of those floating around. Okay. If we add sulfuric acid, this will has the effect of adding H+ ions. So if we add these, the equilibrium will shift to the left. We'll get it more blue. If we add hydroxide ions, this adds hydroxide, which removes hydrogen ions, and so it would shift to the right to replace those hydrogen ions. So maybe it'll get lighter blue. Might go to colorless, maybe not, depends on how much you added. What if you added this XA? So XA is an ionic compound with some other cation. And when you put an ionic compound in water, what it does is it splits apart into ions. And so the effect of adding this XA is that you're going to get more of the anions floating around. The X does nothing, and the reason it does nothing is because X is not in this reaction at all, but the A is, and so adding this compound has the effect of increasing the amount of A, which will shift equilibrium to the left, which would mean it will be more blue. Let's put in here which way these equilibriums are shifting. So this one was more blue, it's shifting that way. Lighter blue, that was shifting this way. Okay. What if we cool the solution and it turns lighter blue? So lighter blue means the equilibrium was shifted to the right. And cooling the solution, that means removing heat. Cooling is removing heat. So that tells you that it's shifting to the right to get more heat or energy, which tells you it must be an exothermic reaction. In other words, this makes sense only if energy is kind of a product, and cooling it makes you want to shift to make more of that heat. Okay, let's look at another example with this compound that's not very water soluble, lead 2 chloride. Lead 2 chloride, when you put it in water, it mainly doesn't dissolve, but there are some of these ions floating around in equilibrium, just not very many at all. But it's there. And so what if we added some sodium chloride? So sodium chloride, when you put it in water, it is very water soluble. And the sodium doesn't do anything, but the chloride ions do. They increase this concentration. So you're going to expect equilibrium to shift this way. So if it's shifting to the left, that means you're going to get more solid. And so you will see that as a precipitate.